Yeah. Boker Tov. Good morning, everyone. Thanks for coming today. It's tough weather. So let's get started. Last time you guys discussed generative models, and today we're going to discuss more generative models. And I plan to give you quite a bit of a taste of new flavors of diffusion models, and especially introduce you to diffusion models, which emerged as state-of-the-art generative models and these days, and we'll talk about it more. And as always, feel free to interrupt, ask questions, and so on. It's going to be, we're going to dive into some math today. Also, not everything is going to be covered in super details, but at the end of the lecture, I can give you also some offline materials if you want to dip in more. Okay, so generative models it's a huge research field. It's and we cannot cover it all. I think you need at least a full semester course to really dive into generative models. But I do want us to kind of like roughly understand what types of generative models are out there. And in general, when we're talking about generative models, we can say that the ultimate goals of these models is to learn the probability distribution of our data. In the case of images, it will be to learn the natural distribution of the distribution of natural images or natural videos or whatever is our signal. And we can roughly divide the type of generative models, those that you've already seen last time, into two general categories. One is never working. Okay. One is the type of generative models that explicitly aim to compute distribution of our data, P of X. And within that category, you guys have seen pixel CNN and pixel RNN, which have a tractable likelihood function, right? We take an image, we break it into discrete elements or pixels or patches, and then we define some ordering between them, and we learn the distribution of a specific pixel conditioned on all the previous pixels that we already generated. And this is tractable. We can explicitly compute the likelihood function. And you guys remember this? Please give me a sign. Yes?
We saw that one of the main things of generative models is that it gives you a specific example rather than a mixture of all the different things. In this case, does it calculate for every pixel the specific, like the pixel from the same, like it chooses the example for the image?
No, you start by you start with a single pixel and you say, given this pixel, what's the probability of the next pixel? And you get a probability density function that you can sample from it. And then you can sample the following pixel and so on. You generate the image as a sequence. And it's very similar to actually what you guys have seen in modeling sequences. So you learn a distribution over the possible pixel values given all the previous ones. And this can be estimated. In the end, the model gives you a real value for the likelihood of a certain pixel conditioned on all the rest. And you guys have also seen variational autoencoders in which you have an encoder that aims, in variational autoencoders, the goal is to map the distribution of natural images into a simple distribution, a Gaussian distribution. And you have this encoder and decoder. The encoder takes an example, maps it into some latent Gaussian vector. And the decoder takes this, you can sample from this Gaussian distribution, and the decoder decodes it into an image. And in this case, the likelihood function is not tractable, but you can approximate it. And you've seen how to basically train a variational autoencoder by maximizing the variational lower bound of our likelihood data, which is an approximation. On the other side of the spectrum, you guys have seen generative adversarial networks in which we don't explicitly aim to compute P of X, but rather we are only interested in sampling from it. Sampling from the data distribution, but we're not explicitly modeling what is the density function of our training data. Okay? And today, we're gonna see more types of generative models. We're gonna talk about vector quantized variational autoencoders, which are aimed to learn a discrete latent space rather than a continuous one. We're gonna talk about vector quantized GANs that also combines the idea of VQ-VAE, the vector quantized variational autoencoder with adversarial training. And we're gonna talk about diffusion models that also falls in this side of models, generative models that are aimed to explicitly compute the density function. Questions? Okay, so let's dive in and start with vector quantized VAE or VQ-VAE. And I guess all the generative models you've seen so far model the latent space in a continuous manner, right? But when we think about it, learning a continuous space could be really challenging because you need that every point in this continuous latent space is going to lead to a valid image sample. And covering all this continuous space could be quite challenging. So the idea of VQ-VAE is to actually learn this Z, the latent space, in a discrete manner. And the intuition is that, you know, even though images are a continuous signal, in the end, our world is composed out of discrete objects, like different types of object categories, different types of object parts. We have all sorts of signals that we might want to work with that are discretized. So that's the main idea, replacing this Z with a discrete latent space. Yes?
So basically what we're saying, instead of auto-regressional, we have auto-classified. So we have lazy classifiers on each and every one of the functions. And then we extract it, decode that. Is that correct? Is that
the intuition is correct. You can think about this idea as that you have an autoencoder, but here in the latent space, in the bottleneck, you basically aim to learn some kind of a function with a discrete function with some nonlinearity that would allow you to map back. And you can learn this with, let's see actually how we can do this. Okay. So the idea is to learn this discrete latent space instead of a continuous one. And one way of representing this discrete latent space is by having a code book. So this code book consists of n latent vectors. Each vector is some vector in some RD space. And we have a final set of them. We set this K. And now the idea is to take an image. As we saw in these, we still have this encoder, which is a CNN-based model, which gonna give us some feature map. And the game now is how to take the encoder output and map it to this discrete code book. So let's assume this encoded feature map, each element here has the same dimensionality as vectors in our code book. So each element in this feature map is a vector in RD. And now we want to be able to map each of these vectors from the encoder output to this code book. Any idea how can we do this?
Integer.
What?
It's integer.
You need to quantize it, but how do you quantize? Because this is a CNN is a continuous function. We're going to get some vector here. Now I want to basically quantize it or relate it or associate it with one element in the code book. Yes? Exactly. You just find the closest one in the code book. So I take my feature from output it from the encoder. I compute some similarity matrix to all my codebook entries, and I take the nearest one. So this is just the nearest neighbor search. And this gives us this Z, which is the nearest neighbor index grid. So let's say that for this vector, the nearest element was the K element in the codebook. Okay? And now I can basically replace each one of my encoded features with an element from the codebook based on the nearest neighbor, and then fit it into a decoder that will reconstruct the image. Okay, the setting is clear? Can you imagine what is the challenge with this design?
You find the codebook.
How do you find the codebook? That's one challenge, yes.
How do you train it if it doesn't pick that codebook at all?
What?
How do you train if it doesn't, like your output initially probably won't pick anything in the codebook at all?
Right, so again, how to learn the codebook, and also the gradients, exactly, because we have this discrete operation here of searching for nearest neighbor, and you know, how do you backprop gradients through this? So let's see it. Just formally, let's define the nearest neighbor operation. So we have ZQ of X, and ZQ of X at some position X, it equals EK if where K is the argmin, it's the nearest neighbor, if we take the distance between our encoded features to each element in the codebook, okay? And again, we have this discrete latent Z that now holds in each position the entry in the codebook that relates each of the elements. And who knows which distribution does this discrete latent variables takes? No, KL divergence is a measurement between two distributions. The posterior categorical distribution is given by by one hot vector here. So this is a discrete latent variable, and its distribution is given by this expression where the probability of Z to be equal to some K, it equals 1 if K is indeed the index of the nearest neighbor and 0 otherwise. Okay? And again, so how do we train this? So obviously, first of all, remember that this is still an autoencoder. So we want this autoencoder to be able to reconstruct our data. So obviously, we need a reconstruction term. So we want basically that if we take this input of the decoder and decode it into an image X hat, we will be able to reconstruct the image X, right? And again, so talking about the challenge of backpropping gradients, you can see that we have this non-differentiable operation of searching nearest neighbors. So basically, there are no gradients floating to our encoder through the reconstruction loss, right? And the way to tackle this challenge is to basically just copy the gradients into the corresponding locations. So what does it mean? Let's say I computed the gradients of the reconstruction loss with respect to ZQ of X. Because these two feature spaces are aligned, this is essentially the same feature space, we can just copy the gradients of the loss with respect to this element into the encoder.
So it's a statement.
It is called straight-through estimator, and it is a well-known term to kind of like overcome this challenge of non-differentiable operations, specifically in this case where basically these two features map are aligned. So we can just copy the gradients. There is now another challenge. If we think about this reconstruction loss, it doesn't even affect our code book because we just copy the gradients from the decoder to the encoder. We don't have any gradients that are going to be used to update our code book. And in order to handle this challenge and to bring into a stable optimization framework, we have two additional terms. The second term, it is called a code book alignment term. And SG here denotes stop gradients. So it means basically that we keep Z of E, whatever in the stop gradients. If you see this notation, it means that stop gradients of X, it means that we, even if X is a trainable parameter or variable, we keep it fixed and we don't backprop gradient through it. So what can you tell me? What does this loss aims to do? Nobody? Okay. So we basically take for each element in our codebook, we take the element in the encoder output that was chosen to be the nearest neighbors of that codebook entry. And we are aiming to optimize the codebook entry such that it will be close to the output of the encoder, right? We keep the output of the encoder fixed, and we optimize E to be closer to the output of the encoder. Yes?
So why is it necessary to perform the stop gradient here?
Why? Because then you will update both. So, that will cause an unstable optimization. Actually, now we have the second term, the third term here in the objective, which is the other way around. It's a commitment loss, and it is aimed to do basically the same, but in the other way around. We basically keep the codebook entries fixed, and now we are aiming to bring the encoder output at the nearest neighbor location to be aligned or to commit as close as possible to the codebook entry. So these two terms in general, they are aimed to bring together the codebook representation and the output of the encoder, right?
E
Yes.
is the nearest neighbor.
What?
E is the nearest neighbor.
Yeah, you see that there is ZE of X. What is X? How do you pick X and E? It's not that you do it with respect to all the entries. So the ZE of X is the nearest neighbor of E is the nearest neighbor of ZE of X out of all the codebook entries. Yes.
Right. So the cookbook loss aims to make the encoder better.
So now let's go over and see
What are the
which components of the math of this framework gets gradients from which. Okay. So the decoder, which loss affects the decoder? The lock P, right. The reconstruction loss affects the basically the decoder. Okay. Oh, sorry, my animation broke. These two losses affect the encoder, right? Because we basically copied the gradients. The decoder gets gradients from the reconstruction loss. The encoder gets gradients from both the reconstruction loss, because we copied the gradients, and also from this commitment loss that is aimed to push it closer to the codebook entries. And finally, our codebook is getting gradients from the codebook alignment loss, which is the second term. Okay, so let's see some reconstruction results. You can see here on the left ground truth images, and you can see here on the right the reconstruction using the VQ-VAE. Okay, so this is great, but how do we generate images? How do we generate images? We learned this discrete latent space, and the idea for generation is that we can, after we train this VQ-VAE, we can now fit an auto-regressive model to learn the distribution over the discrete codebook entries. So I remind you that you've seen that in Pixel CNN, we can learn an auto-regressive generative models by learning the likelihood of a specific pixel xi conditioned on all the previous pixels that we generated. And we learned this by learning this basically categorical distribution over all the possible discrete values that a pixel can take, right, between 0 to 255. Here, instead of learning a discrete distribution over pixel space, we can learn a discrete distribution over our codebook. We have K codebook entries, and now we can do exactly the same as Pixel CNN, but instead of pixels, work in this discrete latency. Okay. So here are some examples of images generated, and I know again this was a few years ago, and 2017 or 19. So, but back then it was kind of like quite an improvement and really a novel way of tackling this the challenge of learning the distribution of natural images. So again, taking this approach of first learning a discrete latent space that allows us to encode natural images into this space, and then we learn an autoregressive models in this discrete latent space. Yes?
I don't understand what the pixel CNN is doing in this case. It's not guessing the next pixel, it's guessing the next what?
The next codebook entry. So let's assume that instead of like images, pixels, I now have at each position, I encoded an image, right? And now in each position, I have some codebook entry. I have some latent code that corresponds to this location. Given, again, I don't want to, if you don't understand, come back. I think maybe it's good that you refresh your memory with Pixel CNN. But in general, like the idea is now that instead of like working in pixel space directly, we work in this latent space, which is discrete. And if I know how to decode an image, use it from this discrete space, I can basically have my generative autoregressive model work in this space, and then decode it back to an image using my pre-trained decoders.
So an image gets turned into a vector?
What?
An image gets turned in the code.
An image, we are generating an image in this latent codebook space, and then decoding it back to an RGB image. And how to learn to synthesize an image in this discrete latent space. This is basically Pixel CNN, only it's not Pixel, it's codebook CNN that learns how to.
But the image in the latent space is stored as what? It's stored as a vector?
Yes, you have a feature map. You see, you have an encoder that decodes it into an image, and each into a feature map, and each feature map is being replaced by a codebook entry. So in the end, you have an H prime by W prime by D feature map, and each RD vector in this feature map is a codebook entry vector. Okay? Yes. Last question, and we are moving on.
What
Yes.
is the motivation to do it, to get into this discrete format of the code? Why does it work better?
So first of all, you can train an autoregressive model on top of it using a discrete categorical distribution, right? It's not something you can do it in pixel space because the values are being discretized into 0 to 255. But working in a pixel space, it's not something that encodes something semantic about the world. It's very local, it's very ambiguous. When you are now encoded an image into this space, which is more meaningful, and it's discrete, you can learn a better autoregressive model in this latent space. Okay? Yeah.
Is this limiting the images that you can predict? Because if you like take a vector from the cookbook, then it'll sort of have like other vectors that like are most closely associated to it, and then we'll pick those ones which will pick the ones which are best matched to them. So you sort of have a deterministic way of picking them, or do you like pick them randomly and then? You
don't sample for, I mean, here you, again.
Like when you're generating, not when you're.
When you are generating, you start with some, like Pixel CNN, you start with some first codebook element. And then condition on that, you want to know what's the probability over the codebook entries, over all these K codebook entries, what's the most likely one, given that I already have this codebook entry at this position. And then you can sample from it, from the distribution over the codebook entry. Yep. Okay. Okay, and then came VQ-VAE plus GAN, which actually boosted the visual quality by quite a bit, and we were able to generate these high quality images. And the main idea here, they suggested two improvements here. So this is, again, the same thing that you've seen before. We have an encoder. The encoder encodes an image into a feature map. This feature map, we are also learning this codebook Z, and everything is the same as we've seen, only that they added the discriminator to not just train the reconstruction with L2 or something like that, but actually have a discriminator that will discriminate the decoded image from realistic images, and that encourages the code book to learn more meaningful representation. The second improvement that they suggested is to replace the CNN autoregressive model with a transformer. So instead of, again, this transformer, you can think about it now that we encoded, we are working in discrete latent space and we are generating an image in an autoregressive manner. It's like learning a sequence, learning sequences. And for that, transformers are, very effective in learning them. So they suggested to have our synthesis is going to be done through a transformer network that, predicts the next token condition on all the rest. Okay. And I should say that, VQ-GAN really showed, again, this significant boost in performance. And Dali, first text-to-image model was actually using this framework of, first encoding the data into this latent space and learning to synthesize through an autoregressive transformer in this latent space.
What is the advantage of transformer? Why to divide it into patches and then learn the sequence?
I mean, this is something you probably discussed a lot in the sequences class with Shai, right? And you learned all about the benefits of transformer, why it's so effective. But in general, first of all, transformer network is something that is tailored to work with discrete sets of tokens, which is what we have here once we encoded an image into a discrete latent space. And second, the big benefit of transformers is that you have this self-attention mechanism, which allows you to compute it to be very expressive. And at each layer or at each such, after each such self-attention layer, basically each token is a function of all the rest. So it's very expressive and can be very powerful and was shown to work better. Okay.
Are there label tags on these images? Like how, when you're going to run the pixel CNN or the transformer to generate to put it pass through the decoder, how do you start that process? Is it just random and all the images trained, or are there tokens to say like?
You need to have the first one. So in the versions of papers that I talked to, the generation or the synthesis is being done as a scan line of the image in an ordering which like zigzagging, and you start with the top left token, and then you generate the following one in a row like scan. So you need to somehow pick the first token and start the generation from there. Follow-up papers actually show that you can do better by just learning not to have an ordered set of synthesis, but rather start with some random token and then compute the distribution of all the rest and pick the one with the highest probability and go on from there. I can give you the reference of that paper if you're interested.
Given multiple types of images, are there meaningful tokens to start? Like, I know that this token is going to be a horse.
Oh, you
mean,
okay.
I was trained on
So,
horses,
right. So you can, I guess you can. A single token probably is not enough to determine the entire category of an image and so on. But the last paper that they showed, the VQ-GAN paper, they also showed how to condition the generative model, all sorts of types of conditioning signals, including categories and so on. Yeah. Okay. I'm trying to decide. Okay, let's start with diffusion models. We're going to take a small break and then continue. Okay. Okay, so some motivation. So diffusion models, they also fall in this category of models that model explicitly or aim to model explicitly the density of our data. And just to give you a bit of motivation, again, all the state-of-the-art basically models that exist out there now are based on diffusion models, including stable diffusion and Imagine, all the video models. We now released this week, I don't know if you saw it, we released from Google a new video model that is called Lumiere. It is also a diffusion model. So really, diffusion models are currently state-of-the-art in terms of generation. And you can see this curve of, citation, number of papers that, use diffusion models. You can see that it's really, it's been quite a revolution in the field of generative AI. And just to show you a bit of the history, so the idea of diffusion models actually arises from was originated in 2015 in this paper, Unsupervised Learning of Statistical Physics. It came from statistical physics. It doesn't have to do with images or visuals at all. And then 5 years later, folks from Berkeley suggested a few improvements, technical improvements, and that really suddenly made a huge jump in visual quality. And here, the revolution of diffusion models and their emergence into the field of computer vision started. 2021, there were, this line of papers that suggested further improvements. This very kind of like diffusion models beat GANs on image synthesis, where they showed with some more technical improvements how, diffusion models are beating every generative model that we've seen before. So that's why it was important for me to also introduce you to diffusion model. Diffusion models also has a wide, it's a broad topic. You can relate it into score-based functions and differentiable equations and so on. We're not going to touch on this perspective in this course. I'm only going to give you the introduction to it from the perspective of what you've seen in the course, which is VAEs. And again, we are going to dive deep into the math, at least for you to see the derivation of how to derive the loss functions of diffusion models and give you also intuitions about what they do. But it's only a very small touch in this topic, okay? Okay, so diffusion models, they, in a very high level, they follow the same concept of taking the manifold of natural images, mapping it into some simple distribution, and then being able to sample from this simple distribution and synthesize images. So this is what you're seeing here. We take an image, we want to encode it into a latent space. You can see that this latent space is a Gaussian distribution, a Gaussian image here. And then we want to be able to take a Gaussian image like you see here and sample from it and decode it into a realistic image. And that's follows exactly what you've seen in VAEs or other generative models. But the key idea in diffusion models is that this encoding and decoding are basically noising processes. So when we take an image and we encode it in the latent space, this is being done by gradually, iteratively taking an image and adding a little bit of noise in small steps, as you can see here, until you get to this final simple Gaussian distribution. And you can think about it that by doing that, we gradually destroy the structure that exists in our natural data until we hit this simple Gaussian distribution. And I really like this 1D illustration that shows it, that we start with this complex distribution of our training data. And each time we diffuse it, we filter it with a Gaussian kernel and move it a little bit towards a Gaussian distribution that by the end of this process, we have this normal Gaussian distribution. And okay, so we talked about intuitively what the forward noising process is doing, the encoding. The decoding is aimed to reverse this process. So we want to do the opposite way around. We want to start with a Gaussian image, the Gaussian distribution, and each time we want to denoise it a bit, just a bit, until in the end of this reverse process, we restore the structure that exists in our training data and basically end up with a sample from our real data. And if we go back to this 1D illustration, so now we start with this Gaussian distribution, we sample some point, and then at the following time step, we got this Gaussian distribution is going to move slightly towards our real data manifold distribution, and we're going to sample a new point from it, and so on, until that in the end of this process, we end up with some real sample from our data distribution. Yes?
What are the points corresponding to this data?
Points that we sampled from this distribution. That's how you generate a real sample from the data. You start by sampling a point from a Gaussian distribution, and then you're going to sample, and then you're going to turn this distribution slightly to a different one, and you're going to sample around this point from the slightly denoised distribution, until that in the end of this process you end up with a real sample from.
But the point is not a full image. It's a point in the image.
What? No, it's a full image. This is just a 1D illustration that shows it for in the case that your data was one-dimensional. Okay, so intuitively you can think about it that, you know, the encoding part is very easy. All you have to do is to take an image and just noise it and noise it and noise it. It's so easy. You don't need to learn anything. But in order to reverse the denoising process, this is actually really challenging, because if you look on this noisy image, how can we separate the noise from the content? You have to have some prior about the world. You have to know that this is a dog and how a typical dog would look like in order to understand what's.
This is the image that you noise. You have this image.
At the reverse process, you don't have access to anything. You have this Gaussian noise and you want to sample an image from it. How do you know how to clean this noise a bit in order to move to the direction of a real image? And this is just for illustration to show how it is being done during training. During test time, you're not guaranteed that even if you take an image, you noise it, you noise it, you noise it. Think about it, that in the end, you destroy all the information that you have in the image. So you don't really have a way of coming back to the same image. You're going to sample another image. For the reverse process, we need a prior. And for the reverse process, we need to learn something about the world. And actually, the forward pass is being fixed. So the entire story about diffusion models is how to reverse the noising process. How do we go from a Gaussian distribution and slightly gradually denoise it such that we'll learn the manifold or distribution of our underlying data. Yes. Go ahead.
At each point, when we go backward, we do have like a snapshot of the gradual noise, the additional noise. I mean, the delta noise we added.
You know it when you're doing the forward process. But
you can use it also during the.
If I give you this image, yes, I want to generate a new image in the world. I have no access to my training data, okay? So we start with some Gaussian noise, and now I want to denoise it. How do I know how to denoise it such that I will end up with, slightly denoised image that actually has some underlying structure that corresponds to a real image?
Okay, so you don't use like snapshots of.
Yeah. And again, you can just stare at this for a second and think about it, that if you don't know anything about the world, you wouldn't do a good job of cleaning the noise from this image. You must know, what are real structures in the world? What is this underlying object? For that, we need to learn a prior, and that's where learning comes into play. So we're going to dive into all the details about diffusion models. We're going to take a 10 minutes break. So please don't be late and come back at 10:05, because we have a lot of math to cover. Yeah, and if you have a question, I can take it now. Okay, so now we're going to dive into each of these, forward and reverse diffusion processes in detail. And we're going to start with the forward diffusion process. So as I said, in the forward process, this is done during training, where we want to basically create this series of noisy images. And we do this by each time adding a little bit of Gaussian noise. And you can see that, if we do that, then we can write the distribution of each forward step, each noising step, sampling from a Gaussian distribution, where the mean is given by this term here, square root of 1 minus beta t xt minus 1, and the variance is given by beta t. And beta is just what is called noise schedule. It controls how much noise we add at each step. And you can think about it as a number between 0 to 1. In practice, you can think about it as a very small number, 0.002 or 1. And it has some scheduling. So we're not going to go into it, but you can change this beta as a function of the time step in the generation. And the goal is just not to basically get saturated values and have so much noise that you destroy right away all the information that you have in the image. So setting this beta t allows to control that. Just a second, and you can think about this noising process and given this mean and variance as just taking the previously noise image, scaling it down a little bit, and then adding more noise to it, a little bit more noise. Yes.
So beta is like temperature?
It's not temperature. It's controlling the intensity of the noise that you add. It's you can see that it's basically the variance of the noise. It's the variance of the noise that you add, and it also controls, the amount of scaling down the mean of this Gaussian. Again, in order to prevent this from getting, saturated and so on. And if we write this forward process as, using each step using this normal distribution. So obviously you can see that, it's a Markov chain. So each xt depends only at the previous sample, sample xt minus 1, and we can write the joint distribution of all the noisy images that we generate in this way, using this just a product between all the pairwise noising steps that we have. Questions? Okay, and so we define this as this Markov chain where xt depends on the previous xt minus 1, and each time we scale it a little bit down and add a bit more noise. But actually in practice, you can, given the clean image x0, we can compute xt in one step. And this is valid because of this property that we are fusing our data with the Gaussian filter. And let's see why this is the case. So again, we have this, to get to xt from xt minus 1, we need to sample from this Gaussian distribution with this mean and variance. And I hope you remember from previous class the reparameterization trick. So we can define alpha t to be 1 minus beta t and apply the reparameterization trick. So xt is basically given by a linear combination between xt minus 1 times squared alpha t plus squared 1 minus alpha t times this zt minus 1. Zt minus 1, what is it? It's just a sample from a normal distribution with 0 mean and unit variance. And you guys remember this from previous class? This is called the reparameterization trick, where using this linear combination, we basically sample from a Gaussian distribution that has this Gaussian distribution, that has this mean and this variance better. Okay? Yes?
One question about the notation. The x of t is a pixel value or like the whole image?
The entire image.
You sample from each pixel, and the mean is like the previous pixel value, or?
You can think about it that, you know, when you can think about it in 1D if it's easier for you, but when we're talking about images, then we basically expand this to 2D. Okay? If it answers the question. No, it's the mean per pixel, you have like a distribution. Okay? And we can apply this recursively, so we can plug in the same expression to xt minus 1 and open, rearrange it a bit. And then if we do that, we have some term that depends on a scalar times xt minus 2. And here we have actually sum of two Gaussians with different variances. And if we need to sum them, it's basically a Gaussian distribution where the variance is the sum of these variances. So if we keep on doing this recursively, we end up with this expression, in which we have a scalar times x0, and this is basically our mean, plus square root of 1 minus alpha bar t times some noise, and this is basically our standard deviation for this Gaussian. So what we see here is that, first of all, alpha t bar is given by the product of all alpha i's. And then it basically means that the distribution, we can define the distribution of xt given x0 now to be a normal distribution where the mean is given by this term and the variance is given by 1 minus alpha bar t. So in order to generate a sample at a certain time step t, we only need to sample from this distribution directly. We don't need to go over all the intermediate steps of generating all the samples until we get to xt. Okay? And again, I'm reminding you that we need to set this noise scheduler. And in this case, we're going to set beta t's such that alpha t, capital T bar, at the end of the generation process will be near 0, because we want to get very close to just a Gaussian distribution. And if we place here 0, right, then we'll end up only with the noise. Okay, so this is basically all I have to say about the forward diffusion processes. And I said the interesting part, that the forward process is quite easy and straightforward. And what we are really after is the reverse denoising step, where we want to be able to somehow approximate this distribution of xt minus 1 given xt, being able to denoise it a bit. Okay, so let's dive in. So again, in the reverse process, the goal is to restore our structure in the data by each time doing these gradual denoising steps. So at each step, we would like to have some underlying distribution that we can sample from, and this underlying distribution is q of xt minus 1 given xt. And the main challenge is that this distribution, estimating it, it's not tractable. We can apply Bayes rule and write it down using this term here, and you can see that we have Q of xt given xt minus 1, which we know how to compute. This is from the forward process, but we end up with this term, which is basically prior on our data, which we don't know how to compute, and it's intractable. But it turns out, so the question is, again, we need a prior about the world, everything we just said about, intuitively. And when we don't know how to compute stuff, the first question that we ask is, can we approximate it? And the answer is yes, in the case of beta t being a very small value, meaning that those forward noising steps, if they are being done in a very incremental manner, then it is possible to show it theoretically that the reverse process can be approximated. It is tractable, and in fact, it is a Gaussian distribution with some unknown mean that depends on the sample at the previous time step and some variance. We're not going to talk much about the variance in this course, basically because we set the forward process to have a fixed variance where we know what is the variance according to our scheduler. We're going to assume that the variance is fixed also in the reverse process, and we can set it up in a way that will make sense. And we're only going to focus on this task of, estimating this unknown mean of this distribution. And the main idea is, again, to train a neural network to predict it, to allow us to approximate or learn what is this underlying mean of the reverse process at each step. Is that clear?
Variance is just another hyperparameter.
What?
Variance is it's a hyperparameter.
Yes. Yes. So we reduce the problem of reversing the diffusion process into a problem of estimating this mean of this Gaussian distribution at each denoising step. And I just want to give you kind of like intuitive illustration of the denoising process. So we have our data manifold. So you can think of the forward denoising process as a process that takes a sample from the data manifold and gradually moves it away from it. And the reverse process is aimed to do the opposite way around. It takes a sample from a Gaussian distribution outside of the data manifold and aim to gradually fuse it and compute a trajectory that will bring it back into a sample from the data manifold. Okay? Okay, so we talked about the intuition, we talked about what we want to estimate. What type of a loss we can use in order to train a diffusion model? So ideally, we would like to maximize the data probability, the likelihood of the data under the reverse process. Problem is, again, that you can see from this intuitive illustration, and also if we write it down mathematically, the probability of our data is given by this integral or marginalizing over the reverse process, which means that we basically, in order to know what's the probability of a certain sample in our data manifold, we need to compute all the different possible trajectories that could end up in this sample from all the possible data points on the Gaussian manifold. And this is intractable. We cannot do that. But you guys have seen in previous class that there is something that is called the variational lower bound, and we can actually bound the log probability of our data using this bound. So we can basically aim to minimize the variational upper bound or maximize the variational lower bound in order to approximate the likelihood objective that we cannot compute. Okay, But and now, so I do want us to go into all the mathematical derivation of how to come up with the final loss that is used to train diffusion models. But before that, I want to just give you, motivation that in the end, we're going to end up with a very simple loss and a very simple training mechanism that goes as follows. During training, you take a sample, a clean sample, you randomly sample some generation time step t, okay? You sample some noise image, and then we do the reparameterization trick in order to compute xt, which is the noisy sample at time step t. We're going to take this noisy sample, we're going to feed it into the neural network. We're also going to feed to the neural network the time step. I didn't illustrate it here. And this neural network is going to predict the noise that was added to this image, okay? And we're going to have just a simple L2 loss between the true ground truth noise that was added to the one that was predicted. And this is, you just take a gradient descent step with respect to this loss to update our neural network. So in the end, this is the objective function, L2 loss between predicted noise and ground truth noise during training. And in order to get that, we're gonna work a bit hard. And just to close the loop, at sampling time after we train this network, how we're gonna generate a new image, we're gonna sample a Gaussian noise image. And then we're gonna start from the noisiest time step to the least noisy time step. And what we're gonna do, we're gonna predict the noise in the noisy image by feeding it into the neural network that we have. We're gonna sample some variance noise and then sample from the reverse distribution, where the reverse distribution is given by this normal distribution with the mean that was predicted from the network and the variance. And we're gonna sample using this formula. And I will just say, if you're wondering, because we are predicting epsilon the noise and not the mean, there is a closed form transformation between the noise and the mean, so it's equivalent, and we'll see it. So we basically just sample xt minus 1 from this distribution using this formula, and then repeat this until we get to time step 0.
Why to predict the noise and not the original image?
So this is a good question. Empirically, it was shown to work better. And I guess it has to do with also the architecture that you use or what's easier for the network to predict. Those models are based on a unit, so it has a skip connection, so it can easily shortcut all the high frequency information in order to get this estimate. Some experience with that, with predicting the clean image or the noise, it was shown that predicting.
Furthermore, if you have the skip connection, so you maintain the original image, so it's better than.
The input is not the original image. The original is the noisy image, and in order from the noisy image to separate the noise and the image content, empirically it was shown that to work better this way. Okay. So let's dive into the derivation of the objective function. So again, we want to be able to approximate the likelihood of the data using the variational lower bound, or what is called evident lower bound elbow. And I remind you that in the case of VAE, again, we had observations, which are images. We had our latents, which was a Gaussian vector. And you guys have seen that the log probability can be bounded by these two terms. The first term is the reconstruction term minus the KL divergence term. So the first term is aimed to reconstruct the data from the latents. And then the second term encourages the latent space to follow some reference probability, which was a Gaussian distribution in the case of VA. Okay? So in our case, what are the observations and what are the latents? In the case of diffusion models, yes?
So your observations just be your noisy image, your clean image.
The observations is the ground truth data, or the clean images. And the latents?
with the Gaussians.
So actually the latents are all the series of XTs that we are, all the noisy versions of the image are latents. So we can just take those and plug them into the equation, okay? All I did is just replacing our observations and latents using these notations. And we can actually write down explicitly the KL divergence term by taking the expectations over this division of the log probabilities. And we can actually join these two terms into one by first taking this minus here and switching the ratio. And then you can see that if we multiply the terms inside the logarithmic, we can just join them into this one term here, okay? Some basic logarithmic rules. So we end up with, the expectation over the log probability, the expectation over the minus log probability is bounded by this term here. And again, I'm not gonna carry on this expectation over Q x of 0, Q x 1 minus t given x0. For simplicity, we're just gonna call it Q, but you need to take the expectations over both your data and the latents in this formulation. And now, given this term, we can again remind ourselves that the joint probability, because we have this Markov chain, can be factorized into this dot product between the different probabilities of each reverse process, right? Because you are doing it. Each denoising step depends only on the previous one, so we can factorize the joint probability of the reverse process into this product and plug it into the equation, and we end up with this expression. Okay? Everyone with me? Yes? No? Okay. And now we'll go over this. No, I'm joking. You can go over it offline if you want. But after, again, some small, more logarithmic basic rules and rearrangement and so on, we can get into this formulation where our objective function consists of 3 terms. The first term is a prior matching term. What does it mean? What do we have here? It's a KL divergence between a fixed Gaussian distribution. So we know that in the end or the starting point of our reverse process, we sample from a Gaussian distribution. So this is P of xt. So this is the Gaussian distribution. It is fixed. We know what it is because this is the first time we start to sample. And this is basically the final noise input in the fourth process. So this term actually, it's just a KL divergence between 2 Gaussians, and it doesn't even depend on the trainable parameters. So we can just omit this term from the objective function. The last term, what is the last term here? It's written. This is a reconstruction term, right? So we want to be able to reconstruct our clean image x0 from the slightly noisier version of it x1. And there is a way, again, following sort of like along the lines of what you've seen in pixel CNN, we can discretize the pixel values and define these categorical distributions over pixel values in order to really compute this. In practice, we can ignore this too. That's what they showed in the DDPM paper, that this term didn't contribute much to the convergence or equality and so on, so we can just ignore this. So we are left only with the middle term. And this term is a denoising matching term. We have a KL divergence again between 2 Gaussians, but let's see what these 2 Gaussians mean. So what is this term here?
One denoising step.
denoising step, yes, this is the one step of the reverse process. And the second term?
Sum of all steps.
No. So this is the distribution of xt minus 1 given xt and x0. So we talked about that without x0, this distribution is intractable. We don't know how to compute it, but because we don't have access to q of xt minus 1, the prior over the entire data. But here, this term, we are also given the clean image. So we are basically asking what's the probability of the slightly less noisy version when we are given both the noisy image at time step t and the clean image. And this, in this case, it is tractable and it actually has a closed form solution. You can compute it analytically. And this again, a Gaussian distribution with a known mean and a known variance that we can compute, which are given by these terms here. Don't be too frightened from all these alpha, beta. These are all scalars, but in the end, the mean is given by a linear combination of the clean image and the noisy image at time step t, with again, all these scalars that depends on the noise scheduling and so on. And the variance is given according to this ratio that again also depends on the noise scheduling and all the dot product. This is the dot product between all the alphas until time step t. So we know how to compute this distribution in closed form. So intuitively, can you say what this term is aimed to do? Yes. Yes, so we basically want, it's a KL divergence term between these two Gaussians. One of them can be considered as the ground truth reverse process, which is Q of xt minus 1 given xt and x0. This is the ground truth reverse denoising step. And the other distribution is the distribution of the predicted reverse
We don't know the clean image.
We don't know the clean image. This is what is being predicted from our neural network. Yes. So it's basically like a data term with respect to the reverse process. Okay. So this is just what we said. In the first line, we have the ground truth. Second line, we have the predicted reverse process and want to match it. So two Gaussian distribution, KL divergence between two Gaussian distributions. So the objective function is given up there, and you can see that it's the expectations over all time steps, right? At each time step, we want to be able to match the distributions of the ground truth reverse process and the predicted one. Let's take a look on one of these KL divergence term. One of these KL divergence term that we denoted by L T minus 1. So this is a KL divergence between two Gaussians, and this is reduced to a regression problem because the KL divergence is reduced to this term here that has basically what we want to do is to minimize the Euclidean distances between the means of these Gaussian distributions, as you can see here, right here.
What is C? What is the constant?
This is a constant. We don't care because it doesn't depend on the learnable parameter. The learnable parameters are all in the mean. We predict the noisy. Let's see why. So again, I showed you a slide back that we have a closed form solution to the mean, which is given by a linear combination of the clean image and the noisy image. But now I want to remind you the reparameterization trick and the way we construct the noisy sample xt from the clean image x0 at the forward process. So this is given by this equation. So we can actually cancel out the dependency of x0 and by expressing x0 in terms of xt and epsilon and plugging it into the term of that defines the mean. And then we'll end up with an expression of the ground truth mean that only depends on the noisy image and the noise. So we can decide that our predicted mean will take the same form, yes, and the only unknown parameters here is the noise. What we need to estimate is the noise, because we have access to XT. This is the noisy image from the current time step that we're trying to denoise. We have access to all these alpha T's and so on that are being computed from the noise scheduling. So our only unknown is epsilon, which is the noise. And if we plug in those expressions to the means into this equation, you can see that we end up with a loss that is aimed to just bring down or minimize the Euclidean distance between the ground truth noise and the predicted noise times this lambda t, which is a scalar that depends on the time step and being defined through some expression that depends on the noise scheduling. And in practice, it turns out that you can even remove this lambda t and not have a noise scheduling and just use this L simple, this simple Euclidean distance between the predicted noise and the ground truth noise. And this is the final objective function that we will use to train the diffusion model. So you need to take the expectation of this on all our data samples and noises and time steps that we add to this neural network. So just to recap, how we're going to train it. So we're going to take an image. We're going to sample some time step and some noise. We're going to use the reparameterization trick to compute the noisy sample at a certain time step t. We're going to fit it into the neural network, predict the noise that was added to this image, and then take a gradient descent step in the direction of the gradient of the Euclidean distance between the predicted noise and the ground truth noise. And during sampling, again, we're going to sample some random noise image and iterate over the time steps starting from the noisiest time step to the cleanest one. We're going to predict the noise in the current image, sample some variance noise, and then sample from the reverse distribution, which is given by this expression, where the term here is what? It's the mean, right? Basically the mean that we saw 2 slides back, that's the mean of the underlying distribution of xt minus 1 given xt. And the variance is being fixed to be equal. In this case, it is said to be equal to the same ground truth variance.
This is done in steps.
Yes, this is done in a loop until we end up with a clean image. And this is just a summary of both training and sampling time and regimes. You can take a look at this again later. Questions? Or you are too overwhelmed? Yes.
So are we just sample from normal distribution to get C? Wouldn't this just give us random noise again?
What? Where?
In the sampling.
Here?
The third step.
Yes, you are sampling this noise, but you are adding just a bit of noise to your clean sample, just because you want to sample from the Gaussian distribution, right? So you are using the reparameterization trick. You need to have a linear combination between the mean plus the variance, the standard deviation times some random noise in distributed with 0 mean and unit variance. So that's what we're doing. This line amounts to a sample from a Gaussian distribution that this is the mean and this is the standard deviation. Yeah. Okay, something that I really like to show, and it gives a lot of intuition of how an image, sorry, another question, yes.
How do you navigate the process to use this type of like you have a very long.
A training time or sampling time?
Something.
You don't.
No, just like.
You sample. You have if you. There are all sorts of ways of adding conditional signals into the process. But if I just follow what I described, which is again this sampling process of starting from a Gaussian noise and diffusing it into denoising it into a sample, you have no control where you're gonna land in the data manifold. It's you get a random image, yes. You sample from, it's like a GAN, right? Local, that you just randomize your latent and you sample from it. You get a sample on your data manifold. So here too, you're not guaranteed. Remember this intuitive illustration that I showed you. You are somewhere on the Gaussian manifold, and now what you learned is a path that will get you back to the data manifold, but you're not guaranteed to go back into a specific point. It depends on how the neural network, how our diffusion model learns to rearrange the space on how it learned this denoising diffusion path, but we don't know exactly how to, what are these paths? Yes.
Even alpha and beta, how do you know how many steps in the forward?
Yeah, it's a good question. And again, setting this noise scheduling, there are a lot of ablations and studies on how to set it and which function this beta T should take, like a linear scheduling, a cosine scheduling, and so on. So I didn't want to go into that, but it's an issue. Like it's one important hyperparameter that needs to be carefully thought of, because again, you can think intuitively that if you destroy all the information way too early, you're going to lose your ability to denoise in the latest time steps and vice versa. So there are all sorts of ways of setting this noise scheduling, and it also depends on your data, on how much structure there is in the data and what types of frequencies exist in data. It's an entire kind of, I don't have a quick answer for that. What I do want to show you, however, is how an image is being gradually generated by the diffusion model. So again, I remind you the reparameterization trick that XT is given by this linear combination of the clean image plus some noise. So we can actually extract the clean image from this equation. And if we think of the reverse process at each step as being generated from something that follows the reparameterization trick, we can visualize the predicted clean image at each denoising step. And here is such a visualization. So I'm going to show you a movie that starts from the noisiest time step, and the clean image predicted from the noisiest time step to the least noisy time step. So it starts with something really low frequency and blurry, as you can see here. And then it gradually adds more and more details and high frequencies to the image. I think it's really gives a lot of intuition of how an image is being built or synthesized through this model. You can think that in the beginning, when you have tons of noise, you don't have this information about high frequencies or the underlying detailed structure of an image. So in the beginning, the diffusion model diffuses it, but it's only able to generate this really rough, low frequency image that gives you roughly the blobs and the layout of the image. And then once you add more and more details, it refines its synthesis and estimation and adds more and more high frequencies to the generation. In terms of implementation, just again, a small comment about that. So as I said, current architectures follow a unit design where we have skip connections. The resolution is maintained. You see that the input resolution and the output resolution is the same. We're really working in this pixel space. And that's why it's important to have the skip connections, and the time step of the generation is being encoded into some vector using some fully connected layer, and then being injected to all the layers. There are different techniques of injecting it. It's either you really edit element-wise to your features, or there is some way of editing it through some normalization layers.
Time representation is called as a cosine.
So are different ways, either cosine or you can just fit it. Yes, you basically map it into some vector, and then you have some maybe fully connected layers to learn the embedding and to map it into the right.
That's also learnable.
What?
That's
Yeah.
also learnable as well.
Yes. And one issue with diffusion models is that generating an image sampling takes a lot of time. You have to go through all these iterative denoising steps. You cannot just synthesize an image in real time like you can do with GANs. So again, some ablations, we're not going to go into all the details, but this is the measurements of image quality. And this is the number of sampling steps. So it turns out that you can actually skip some steps at inference time and just generate an image with less steps. So you can see that it plateaus at some point. So adding more denoising steps, it doesn't improve the generation quality. So in practice, we can use much less denoising steps than we would have theoretically. Okay. And again, with some more engineering tweaks and architectural changes and scheduling, really OpenAI kind of like push the boundaries of the quality that you can get with diffusion models, and you can synthesize this great images. And I think the main advantage of diffusion models is it doesn't suffer from this mode collapse issue that GANs suffer from, and therefore it's much easier to learn really complex distributions, like again what we learned today with text and image diffusion models. And in that sense, it brings me to just kind of like explaining very briefly how we add some conditioning signals. So in text to image and image generation, you want to add an additional conditioning signal. Could be a caption, it could be another image, it could be a depth map. We want to condition the generation in some other signal. So instead of modeling the probability of our data, we want to model the conditional probability of our data given our conditioning signal. And it turns out that it's really easy to do it with diffusion models. So let's see an example of super resolution. I want to be able to take a low-res image and predict a high-resolution image. So all I have to do is to take this low-resolution image, by linearly upsample it or naively upsample it, and concatenate it with our input. That's it, and train it to reconstruct the ground truth high-resolution image, as we did before with the same objective function. In terms of introducing this conditional signal just by concatenation. Why it's so easy, why it makes sense why it cannot just ignore the conditioning signal.
Just to incorporate them together, right?
But it can ignore it. It can learn that it's not a meaningful signal and just ignore it.
Then it couldn't reconstruct it, right?
I didn't change the objective function. All I care is about reconstructing my ground truth data. I didn't say anything about, the conditioning signal. The reason why it won't ignore it is that you have to think about the noisiest time steps of the generation. In the noisiest time steps, this will be almost no structure, just noise. So, and the model needs to learn how to reconstruct an image. So this will be valuable information for this neural network to complete its task of denoising the image. It doesn't have any knowledge about the image itself because this is so noisy that it hardly has any information about what the image it should synthesize. But the conditioning signal, even in the noisiest time step, has a lot of information that the network can use in order to learn how to denoise this really almost noise input image.
Are you concatenating them or
Concatenating.
Okay.
Yeah. Okay, so it turns out that again, just by concatenating a low-res image into the inputs of the diffusion model, can get some really nice super resolution results. And you can, in this case, they stack the few models together, like they train one diffusion model that goes from 32 to 64, and then another model goes from 64 to 56. It's a cascaded approach. Yes?
You in the process, you're not adding noise to the Y?
You're not adding noise to the Y because you are interested in preserving the information that you have in Y.
Mm-hmm.
So adding noise will remove information, destroy information from it. You want to preserve it in this case. More results. And it turns out you can also do all sorts of image-to-image translation tests, again, just by concatenating conditioning signals, like, for example, a grayscale image or a masked image in all sorts of different types of masks. Questions?
Here the input is gray and the output is this 4 samples.
You condition your diffusion model on a grayscale image, and the model is trained to learn the distribution of natural images. For a grayscale image, you might have multiple solutions for what is the color image.
Yeah.
So when you are sampling, you can sample different samples by starting from different noises, right? Like if I start from one random noise, X capital T, or another one, I'm gonna end up with a different sample. But in all cases, you can see that it adheres to the conditioning signal, which is the grayscale image. And again, the intuition is that in the noisiest time steps, this is the only information that the model have on how to denoise this image. So it's using it. Okay, I think we basically are done. Just want to credit Yaniv, Rafael, and Omer as my students, and Rafael and Yaniv, you know them. They helped me to gather the materials for this challenging lecture, but I hope you enjoyed it. Next class, it's going to be me again, talking about self-supervised learning. And I guess I have time a little bit few more minutes for questions. So if you have any or are interested. Yeah.
So if you're at every step introducing a little bit of noise when you denoising, could you maybe instead of doing it linearly, you could have you do 5 different predictions and then you concatenate all of them, and then you have more denoising going on.
What do you mean?
Instead of having it
oh, I see. You want at each step, you want to add 5 different noises, denoising it under 5 different Z's, and then somehow aggregate the results.
Yeah.
It's an interesting thought, but I think that you have to think about it that, again, you are sampling from a distribution, and at the pixel level, you're not guaranteed that things are going to be aligned. So you saw that, for example, in the coloring example, the amount of the seed that I started with, the different noises that I started with, end up with a completely different colored image. So if you're going to average those predictions, you're going to get a blurry image out. But maybe there is something that is called restart sampling, which means that right now I showed you that when we are sampling an image, at each denoising step, we are only doing one step. You have a noisy image, you denoise it, you move to the next time step. But it turns out that you can improve the predictions a bit if you repeat a certain time step more than once. So you took a noisy image, you denoise it, you add noise again, you denoise it again for the same time step, and then you move on to the next time step. So it follows a little bit your intuition about maybe getting predictions from multiple time steps from different noises. So, yeah. Thank you, guys. Thanks.